All right, so now we're going to do a two-dimensional momentum problem. And this momentum problem is going to be fairly straightforward, but it's going to be in two dimensions, which makes it quite difficult. We're going to start with an object that simply isn't moving at all. We're going to have that object have a mass. So let's say that it has 10 kilograms total mass, and it's not moving. That means that its momentum is 0 kilogram meters per second before something happens. And what we're going to do is we're going to just embed this object with some contact explosives, and then we're going to set off the explosion. Okay. So after the explosion, we've got three objects. And so one chunk of this thing, okay, let's say it was, I don't know, say 4 kilograms. And this, by the way, is a helicopter view. We're looking down at it. And let's say this 4 kilogram object blasted off and it's going directly north. And let's say that it had a velocity of, what would you like, of 50 meters per second. Okay, it's a big explosion. We want things going a little faster. So we'll have it going 50 meters per second going north. We're going to have another chunk. Let's have it be, you know, a chunk over here that came blasting off of that. And let's have it also be, say, 4 kilograms. And this 4 kilogram chunk, unfortunately, as far as our math is concerned, went flying off at an angle. Okay? And so it's going south, and it's also going west. And let's say that it's going south of west at, looks like, about 40 degrees. Okay? Let's say that the speed that it's shooting off there is similar to the other one. Let's have it going, say, 40 meters per second. Sounds good. Okay, so we have these two objects. Now, we don't know about the third object, and the question is, what is that third object? It broke into only 3 pieces. I'm not showing the third object. It's clearly, you know, initially over in here somewhere. But that third object, the question is, how fast is it going, and in what direction is it going? Okay, so that's our question. We started with a 10 kilogram object sitting there not moving. It exploded into 3 pieces. 2 of the pieces are known. One is going north, exactly north, with 4 kilograms and with 4 kilograms and 50 meters per second. The other one down here is going off at 40 degrees south of west. And those 2 pieces of information are enough information for you to determine what this third object is going to be doing. Okay? So that's the problem. Let's get started. First off, I hope we can all deduce the mass. Right? Good. So we understand that it's 2 kilograms. Excellent. And I hope you all have a feeling that it needs to be going east to some degree. Right? It should feel like it needs to be going east and maybe north or maybe south. It's hard to tell there. Okay, maybe a little bit south, but we're kind of guessing. We're not sure. Okay, so in order to figure that out, what we're going to do is we're going to take the momentum problem and think of it in terms of components. We're going to look in terms of north and south, right? What's going on with north and south? As one problem, we're also going to be looking in terms of west and east and what happens in that in terms of momentum. Okay, so let's go ahead and find the components of this one at an angle. We'll need to know that. So we have our west component and we have our south component. And you can get your components of the velocity or you can get the components of the momentum. It doesn't matter. It's easier, in my opinion, to immediately go to momentum. And so that's what I'm going to do. I'm going to go to momentum first. So I'm not going to use the 40 meters per second here. I'm going to immediately go to momentum. And so I'm actually going to have 4, right, times 40. So I have 160 kilogram meters per second along the hypotenuse. Okay? And then what I need is these 2 components. I need to know both the west part of the component as well as the south part of the component of this original 160. Okay? So sine 40 times 160, and we can get the south component. Anybody have that? So let's just call it 103 kilogram meters per second. And then the western component with a cosine, right? We do cosine of 40 times 160. 123. Oh, so this one we got 123 kilogram meters per second. While we're here, I hope it's clear that the momentum north on this guy up on top here is going to be 4 times 50, so 200, right? Kilogram meters per second going north. And now it's time to stop, slow down a little bit, and think. Yeah. Beautiful. North and south cancel. And the 200 that we need to cancel the north is going to be canceling with the 103. Exactly. So we need another south of 97. Because we need the souths to add up to 200 and the 200 north. So what we've already determined is that on this 2 kilogram, we knew it had to go east. That was pretty obvious to us. But now we also know that it needs to go south. And the momentum south needs to be 97. And we need that so the 200 north and 200 south cancel, right? East and west is pretty easy too, because we've got this 123 west, and I got nothing else, right? So exactly, I'm going to need 123 east. Notice please, after we took the component, we never ever again will use that 160. That 160 is not used again, okay? Because we're not using the 160. Instead, we're using the components, okay? So like we said, we've got 123 east in order to cancel the 123 west. And we've got 97, we said, right? 97 kilogram meters per second south, which gives us our overall momentum for this 2 kilogram object needs to be going south and east. And so we use Pythagorean theorem, we do arctangent, and we can get these numbers. So on the hypotenuse here, spend a minute doing Pythagorean. 157. Okay, so that should round around 157. One thing that's interesting here is our numbers can be slightly different depending on whether we use rounded numbers, we use the original number before rounding. So you can have slight differences there. And the angle, excellent, south of east by an amount that if we did an arctangent on this, looks like it's a little bit under 45, 38. Somewhere around 38 degrees. Again, depending on where you rounded, you should have something around 38 degrees. Yeah. Okay, so that's an excellent question. The question that was asked was, since the 200 was bigger, right, than the south one, shouldn't the north have won? Okay, and the idea here isn't about who's winning. The idea is about getting to where we started. And where did we start? We started with the momentum of 0. Okay, so since we started with the momentum of 0, that means that our momentum north, completely totaled, right, which is 200, must equal, we have no choice. It must equal the momentum south. So we have 103 is not enough. So we add that to the 97. Now it is enough because now we have a total of 200 south. Great question. Now, we feel like we're done, and on, when you're taking an exam on this, like this type of problem, you've done a lot of work. You feel like you've done enough work to deserve the points for this problem, and you'd like to say, okay, I'll go on to the next question now. You feel like you're done, but you're not. Because the question asked for the velocity of that third piece. And what we have found here is not a velocity. This 157 here is a momentum. And so we need the velocity of that guy. So we have one last thing we're going to have to do, and that's to say that since momentum is mass times velocity, that velocity is momentum divided by mass. And so we can take our 157 and divide it by 2. And so we get right? So around 70, we'll call it 78 meters per second at, and we're really careful to say 38 degrees south of east. And hopefully I didn't make a mistake there. Are we agreeing on the numbers here? Excellent. And so while this is a two-dimensional problem, which makes it kind of tricky, please realize it's kind of an easier two-dimensional problem. And the reason is the initial object wasn't moving. And so that made things real simple in the fact that all the momentums had to cancel, and that kept it clean. If this original object had also been moving, that would have made make the whole problem more difficult. And so I'll probably do one of those as well as an example. But you're for sure to see this. I often give this problem that we just did here in terms of a raft. And so this is very similar to the raft problem that you might have done in studying for this next test. In any case, good luck. I hope that helps. And if not, come and see me at lunch. Thanks.